What makes a nuclear bomb tick? Presented by Tim Lyons. Thank God it's complicated. While tech development has sped up at an exponential pace in the past 50 years, we are fortunate that it's still technically challenging, time-consuming, and expensive to build a nuclear bomb. The following presentation explains what occurs in the nuclear chain reaction and what components are needed to make this cataclysmic release of energy possible. So, where we're going in this presentation. First, we're going to talk about nuclear bomb basics. What's inside that shell? Then, there's uranium and there's uranium, as Seinfeld would say. We're going to talk about the difference between U-238 and U-235, which is a very important distinction. Lastly, we're going to talk about enrichment schemes, how gas centrifuge became a dirty word in international diplomacy. So, nuclear bomb basics. The goal of a nuclear bomb is to unleash the nuclear binding energy of uranium through fission. A basic reaction for uranium is U-235 plus a neutron generates strontium-90 and xenon-143 plus 3 neutrons. And this is very important to note. 1 neutron in, 3 neutrons out. Plus 2 times 10 to the 13 joules per mole, which is an enormous amount of thermal energy compared, for example, to the combustion of coal, which is only 5 times 10 to the 7th joules per ton. However, the strength of that reaction is not the only thing that makes uranium such a powerful fissile material. When U-235 splits, it causes it can trigger what is called a nuclear chain reaction. When U-235 splits, it emits more neutrons, which collide into more U-235 atoms, causing them to split and emit more neutrons, which collide into more U-235 atoms, and so on. Within 1 second, this reaction can become uncontrollable, as long as there is enough U-235 present to sustain the reaction. Critical mass is what we call the minimum mass of fissionable material required to generate a self-sustaining nuclear chain reaction. A subcritical amount is an amount that it doesn't reach critical mass. So as you can imagine, when you have a bomb, as you see here on the left, you don't you don't allow a critical mass to exist in one clump. You separate it into 2 subcritical masses. The critical mass for, an example here, the critical mass for a bomb that is 85% highly enriched uranium is 50 kilograms, or a sphere about 17 centimeters in diameter. The first bomb dropped on Hiroshima was Little Boy, and as you can see from the schematic below, it used this type of design, which is called a gun-type fission weapon. It's called that because in order to produce a detonation, the subcritical pieces of uranium are brought together rapidly through a gun barrel. In Little Boy, this was achieved by firing a piece of uranium down the barrel into the piece at the other end. You can see the conventional explosive is at the nose of the bomb. When it explodes, it causes the first piece of uranium to fire down the gun barrel into the second piece of uranium. So what is the difference between U-238 and U-235? U-238 is the most common isotope of uranium. It represents 99% of what you find in a piece of natural uranium. It's non-fissile, although it can be transmuted into plutonium-239. U-235, on the other hand, is highly fissile. It is the only fissile isotope that is found in any significant quantity in nature. It makes up 0.78% of natural uranium. So, uranium, as you can imagine, needs to be enriched so that it's richer than 0.78%. The goal of uranium enrichment is to increase the concentration of U-235 in a bunch of uranium from 0.78% to 3.5 to 4.5% for nuclear reactors, or to 85% for nuclear weapons. There are two processes that can be used for enriching uranium: gaseous diffusion and gas centrifugation. Gas centrifuges represent nearly 100% of are responsible for the production of nearly 100% of the world's enriched uranium today. Uranium hexafluoride gas is spun in these centrifuges until the heavier U-238 is pulled to the outer edges of the cylinder. Each cylinder's rotation creates a strong centrifugal force, and it separates the two of them. Centrifuges and non-proliferation. So the most difficult step in building a nuclear weapon is the production of fissile material. So the most difficult step is the enrichment process. Improvements in gas centrifuges have made it easier than ever. The gas centrifuges are faster, less expensive, and easier to hide than previous methods that were used to enrich uranium. This makes it very challenging because it's also challenging because the same centrifuges are used for peaceful purposes, like generating enriched uranium for nuclear power plants. The International Atomic Energy Agency, the IAEA, attempts to promote safe, secure, and peaceful use of nuclear technology. In closing, nuclear bombs unleash the nuclear bonding energy of U-235. Nuclear chain reactions take place when a critical mass of fissile material is present. U-235 is fissile. U-238 is not. Gas centrifuges are used to increase the concentration of U-235 for both peaceful purposes and for nuclear weapons. This technology makes non-proliferation more difficult.